Alright, today I'm gonna talk about ANOVA. This is the main topic for today's lecture, but before doing that, we need to first finish up some leftover from last lecture. In the last lecture, we covered the one sample and the two sample test for the population mean, but we didn't get a chance to talk about the test for proportion. So today, let's spend some time to finish up this proportion test. I'm gonna only talk about the test for proportion for one sample. And we will talk about two tests. One test is the z-test for proportion. This test gonna be used when the sample size is large. And the other test is gonna be used when the sample size is small. We call it exact method using the binomial distribution. So let's start with one example. For example 1, if you are an accounting manager, a year-end audit showed that 4% of transactions had errors. You implement new procedures. A random sample of 500 transactions had 25 errors. The question is that, has the proportion of error transactions changed? You are suggested to use 5% significance level to perform the test. So this is a problem about the proportion. We first need to write down the null and alternative hypotheses. You see, previous error transaction, proportion of error transaction is 4%. So we want to compare the new error proportion to this number. So we put 4% in our null hypothesis. Under the null, we put the population proportion equals to 4%. And we want to show whether our new procedure has effect or not, whether the new proportion of error is different from 4% or not. So the alternative hypothesis, we have P doesn't equal to 4%. This is gonna be a two-sided test, okay? For the first example. The second example, a researcher claims that less than 20% of adults in the US are allergic to an herbal medicine. In a simple random sample of 25 adults, 3 say that they have such an allergy. Does this support the researcher's claim? Yet the researcher wants to show that this proportion of allergy is less than 20%. This is his research goal. We should put P less than 0.2 in the alternative hypothesis. And under the null, we should put the proportion equals to 20%. Is that okay? So this is another example. This test gonna lead to a one-sided test. So since we are talking about proportion, recall that we learned that if X denotes the number of success from n trials, then X is a binomial distribution. X follows a binomial distribution with the total number of trial n and a success probability p. For this binomial distribution, we know its mean just equals to the total number of trials multiplied the success probability, and its variance is given by n times p times 1 minus p. Okay, so from this binomial distribution properties, we also know that the sample proportion, x divided by n, we call it p hat. This sampling proportion is an unbiased estimate for p, the population proportion. And we also know the properties for this sampling proportion p hat. Its expectation is equals to the 1 in the population proportion p. The variance of p hat is p times 1 minus p divided by n. If we know the expectation of variance of p hat by the central limit theorem when the sample size is really large, we know that p hats follow approximately normally distributed, with a mean to the population proportion p and the standard error or standard variance or sampling variance to be this number. Is that okay? So we have learned this part in the previous lectures. So we're gonna use this property, this approximately normally distributed distribution to derive the test on the sampling proportion. So generally speaking, we are dealing with one sample proportion test. Its hypothesis is written in this way. Under the null, we put a P0 for the population proportion. And under the alternative, we let it doesn't equals to this given number. And the following test must have such assumptions. First, we have two outcomes, fail or success, 0 or 1. And then we can use the proportion to summarize the data. Another condition is that the number of success follows a binomial distribution. And the normal approximation should be used whenever this quantity, n, the total number of trials, multiply the P0, the value you put on your null hypothesis. This is under the null what you believe the population proportion equals to what? N multiply P0 times Q0. Q0 is just 1 minus P0, the failure probability. This quantity, if greater than 5, this is whenever either sample size is really large or P0 is around 0.5, it's not on 0 or 1. So then this quantity should be greater than 5. Whenever this quantity is greater than 5, we can use the normal approximation to approximate that statistics we're going to talk about next. Okay, so this is the quantity. One, this condition, one, the sample size is really large, one, this condition is satisfied, then this quantity is normally distributed. This is how did we get this quantity? We just using the sampling proportion p hat minus P0. This is the number under the null hypothesis. We put it here, right? Under the null hypothesis, we believe the population proportion is P0. And if the null hypothesis is true, then the expectation of P hat should equals to P0. This is what we are always talk about under the null hypothesis. Then we use the P hat minus its mean divided by its standard deviation. This is this quantity. And then we call this statistics, these statistics. This statistics under the null hypothesis is normally distributed. Actually a standard normally distributed. Okay, then after we know that the distribution for this Z quantity, using this example, I'm gonna show you how to determine whether this hypothesis is true or not. So back to this accounting problem, we have the null hypothesis, P equals to 4%. Alternative hypothesis, it doesn't equals to 4%. We know that the significance level is 5%. The number of trials is 500. For this specific example, the first thing we need to check that the quantity n times P0 times Q0, whether it's greater than 5 or not. If greater than 5, we're gonna use the following procedure. Otherwise, we need to use the exact binomial method. So you can see for this example, n times P0 times Q0 is 19.2, greater than 5. Then we're gonna use the Z test, the standard normal test. So then, next step, we calculate this test statistics. P hat, you can get this estimate, use your sample. P hat, because we draw 500 transaction, randomly selected 500 transaction, 25 out of them has error. So we are talking about the error proportion. This is the P hat, the estimate using the sample, okay? Then minus the P0 you put in your null hypothesis, and also the standard error calculated using the P0, because we are talking about the underlying distribution for this Z under the null hypothesis. So this quantity equals to 1.14. This is our observed Z statistics. We're gonna compare it with our critical value. Because this is a z-test, this quantity follows a standard normal distribution. We know the 95% confidence interval or just a 5% significance level. The critical point for it is 1.96, right? This number you should memorize it. For the standard normal, the 5% significance level, the critical value for two-sided is 1.96, around 2. And then after determining these critical values, you have these two rejection regions on the two tails. Then you just check whether your observed z-statistics fall into that rejection region or not. 1.14 less than 1.96 is in the middle, is not in the rejection region, so we do not reject our null hypothesis. The decision is we do not reject null hypothesis. The conclusion is there's no evidence this proportion has changed from 4%. Is that okay?
So you have to assume your data has a normal distribution to apply it, basically.
This is one that we check this condition, n times p0 times q0. If this number is large enough, we can using the normal distribution to approximate the distribution for p hat.
Wait, sorry, okay. No, that's not the assumption. Because the central limit theorem says that whatever the distribution of the underlying data is, their means will follow the normal distribution. That's what it means.
Yeah, when the sample size is large enough, the central limit theorem guarantees that we can using this, we can derive the distribution for this z quantity under the null hypothesis is standard normal. Any other questions? Then okay. So now let's look at example 2. For this example, the researcher claims that less than 20% of adults in the US are allergic to herbal medicine. And then we draw a simple random sample of 25. 3 of them said that they have an allergy. So you just using this sample data to check whether the researcher's hypothesis is true or not. This is another example for the test for proportion. The first thing you need to check this quantity, n times p0 times q0, whether it's greater than 5. You can see in the sample we have 25 samples, and the success probability we're gonna put under the null hypothesis gonna be 0.2. So times 0.2 times 0.8 is 4. It's less than 5. The central limit theorem cannot be applied because the sample size is small. So what should we do? Here is just a distribution for a binomial distribution with n equals to 25. Success probability is 0.2. You can see its distribution is skewed. It's not normally distributed. So this shows that actually when n times p0 times q0 less than 5, we cannot use a normal to well approximate this sampling distribution for p hat. So whenever this happened, we're gonna use the exact method based on binomial distribution. We know x, the number of success, is binomial distributed. Okay? So whenever the sample size is small, this quantity less than 5, depends on your alternative hypothesis. We will be able to calculate the p-value. First, 1p, the population proportion less than p0 in your alternative hypothesis. If you assume that actually this proportion should be less than that given number, we can calculate the p-value by looking at this probability. X is the number of success in this binomial trial. And a small x, this small x is gonna be the observed number of success in your sample. Remember, what's the definition for the p-value? The p-value is the probability for you get a number as extreme or even more extreme than your observed value, right? So if you get small x number of success in those n binomial trials, what's the probability for you get a number of success as extreme or more extreme than x. That is a probability less or equal than small x in those n trials given the null hypothesis is true. Is that okay? So this less or equal than is determined by your alternative hypothesis. Your alternative hypothesis, you said that you believe this proportion is less than p0. So that means the extreme point should be occurs on the lower tail. So then the 1p in alternative hypothesis, p less than p0, the p-value should be calculated in this way. And x is a binomial distribution. We know this cumulative probability should be calculated in this way, right? Big X less or equal than small x is the summation from 0 through to x, then using this binomial formula. And in Excel, you can using this function to get this cumulative probability for p capital X less than small x. Is that okay? Here, there are 4 elements in this function. The first function, just you observed number of success. N is total number of trial. P0 is just a success probability. And the first elements you put true here. If true, that means you are calculating the cumulative probability. If false, it's just give you the density, just give you the probability for big X just equals to small x when you put the first elements to be false. Is that okay? So same thing here. If you put alternative hypothesis, you believe the proportion is bigger than this p0, then your one-sided p-value should be the probability of capital X greater or equal than small x. Your belief in your alternative should occur on the big value, larger value, on your right tail. Then your p-value, when you look at the p-value, you should also calculate the probability beyond this small x on the right tail. And here is this is the exact formula for your p-value. And here is the function, Excel function you need to use to calculate this p-value. Here we just use 1 minus the summation k from 0 to x minus 1. Because here we need to include the probability for x equals to small x up through to n. Then you just 1 minus the composite of it. Okay? And here, before we're talking about the real example, here is how to calculate the p-value for the two-sided test. For the two-sided test, depends on your proportion, sampling proportion estimates. In your sample, if your sample estimate is less than p0, the number you put under the null hypothesis, then your p-value just calculate the lower tail probability, then double it, gonna be the two-sided probability, two-sided p-value. Because for the two-sided test, the extreme points could occur on each tails, each end. Depends on your observation, the sampling estimates p hat. If less than p0, then your observed value gonna on the left tail. Then you look at the probability on the left tail, then double it, gonna be your p-value. In the other hand, if your p hat is greater than p0, then your p-value it should be calculated on the upper tail, and the right tail. Was that probability beyond your observed small x? Then you double it, gonna be your gonna be the p-value for the two-sided test. So now let's look at how to implement this exact binomial method using example. Back to this example, we know we have 25 simple random sample, and three of them said that they have an allergy. We first get a p hat is 3 over 25. Then we need to put put our hypothesis, null hypothesis is P0 equals to 20%, 0.2. And in our alternative hypothesis, we let P less than 0.2. Okay? Because in the alternative P less than P0, we need to calculate the p-value from k from 0 to 3. 3 is our observed number of success. P less than P0, we only count the probability smaller than x, smaller or equal than x. Then this is the summation from 0 to 3 of those binomial quantities. And this quantity can be obtained by this function in Excel. And this gives us the number 0.234. This is the p-values based on the exact binomial distribution, binomial method. This p-value is bigger than our significance level 5%. Then that means this test, the null hypothesis, is not significantly rejected. So the conclusion is that there's no evidence that the proportion is less than 20%. Is that okay? This is the test for proportion in one sample. Here, before I move on to the ANOVA, this is just a review of all the hypothesis tests we have covered in today and the last lectures. We talk about one sample test for population mean, mu. And whenever the population standard deviation sigma is known, we're gonna use the z-test. If the population standard deviation is unknown, we're gonna use the t-test. So here is the trick is that depends on the population variance or population standard deviation sigma is known or not. If known, we always use z-test. If unknown, we always use t-test. In practice, this sigma is always unknown, so most likely, most common used test is the t-test. Okay? And then for the one sample test for population proportion, we just talk about that. Depends on this quantity. N times P0 times Q0. If this number is bigger than 5, we can use the central limit theorem to get the normal, approximated normal distribution. We can use the z-test. Otherwise, we need to use the exact method, calculating the exact p-value using the binomial distribution. Then, for the two sample test for two population means, still first we depends on these two populations, they are related or not. If they are related, either from the longitudinal study or match the case control study, we need to use the paired t-test. If those two samples from two independent populations, we're gonna use the t-test using two t-tests from two independent populations. And whenever the sigma is known, actually this is rarely happen in the practice, we can use the z-test. Usually sigma is unknown, we always use the t-test. And for the independent two samples, we need to first determine whether the variance from those two populations, from those two samples, they are equal or not, using the two sample test for difference in population variance. That is the F-test. Using F-test, first determine whether the variance from those two populations, they are the same or not. If they are same, we're gonna use the t-test with equal variance. Otherwise, we use the t-test, two sample t-test with unequal variance. Is that okay? This is all the tests we have learned so far. And then next, we're gonna talk about analysis of variance. Analysis of variance is a test about multi-sample inference. So far, we only talk about the population mean or proportion from one sample or two samples. We compare the means from two samples. But whenever there are more than two samples, more than 2 groups, if we want to compare their means, we're gonna need to use this ANOVA test. ANOVA test is for the multi-group comparison. Is that okay? So whenever we have more than 2 groups of individuals, say we test the groups were sampled from distribution with equal population means, ANOVA gonna test on this whether the means from different groups, more than 2 groups, they are equal or not. So because here say we have k groups, more than 2, and in the null hypothesis, we assume all the population means they are equal. There's no difference among those groups. And here, what's the alternative hypothesis? The alternative hypothesis is not that all population means are different. No, actually, it's that it is not all of the population means are the same. At least the one population mean is different, then we reject the null hypothesis. Okay, so here, this is the situation. All of those k group, their population mean are the same, then we say there's no treatment effect. There's no difference among those k population mean. We do not reject the null hypothesis. Whenever there is at least one group mean is different from the others, we're gonna reject the null hypothesis. At least one group mean is different from the other. This is our alternative hypothesis. Whenever we reject the null hypothesis, we say at least one group mean is different from the others. For those either of the situation, we're gonna reject the null hypothesis. For here, 1 is different from the other 2, we reject the null hypothesis. This one is all 3 are different, then we still reject the null hypothesis. Okay? So here is the assumptions for the ANOVA test. Those k random samples, k group random samples, should be drawn from k independent populations. Those k groups should be different, should be independent. Okay? And the variance of the populations are identical. That means we assume the variance from each group, they are the same. The variance, the sample variance or population variance, for each group, they are the same. This is the underlying assumption for ANOVA test. And the underlying data are approximately normally distributed. Then, how to perform the ANOVA test? Here I just elaborate the basic idea for the ANOVA test. We first let Yij to denote the jth observation for the ith group. Okay, Yij, I index which group it belongs to. J is indexed to the number of observations in the ith group. Okay, Yij. Then Y bar is the overall mean across all the samples of those k groups. What's the overall mean of it? We denote it as Y bar. And the Yi bar, there's a I here. This I index the ith group. Yi bar is the mean of the ith group. Then we look at a specific observation for the jth observation in the ith group Yij. We can rewrite Yij into this equation. That is Y bar, the overall mean, plus this difference. This difference is just a group mean minus overall mean. And plus the third term is this Yij minus its group mean. Is that okay? You can see actually we plus Yi bar minus Yi bar plus overall mean Y bar minus Y bar, those can be cancelled out, still Yij. But in this way, we can partition the variance, the overall variance, into different parts. You will see later. So here you understand how did I get this equation, right? So you can see Yij actually looking at these pictures. For one specific sample, you can see one specific sample if it minus y bar, the overall mean represented by this red line, overall mean y bar, the difference from each individual to the overall mean equals to what? Equals to, we first look at this individual, what's the difference for this individual from its group mean? That is yij minus yi bar. Then plus this group mean, the difference, the distance from this group mean to the overall mean, yi bar minus y bar. Is that okay? So the difference between each individual to the overall mean can be partitioned into these two parts. The one part is the deviation of observation from group mean. We call it within group variability. The second part is the deviation of observation from overall mean. This is between group variability. Okay, then continue from this equation. If we square on both sides and then do the summation through all the observations, we can get, how did we get this equation? From there, we just square on both sides. Then do the summation through all the observations across those k groups. Square it, then do the summation. The left part is the total variation. We calculate the total variation from each individual to the overall mean. We call it total variation. And the right part, it still have two parts. When you square it, there's a cross term. Actually, when you do the summation, that cross term equals to 0 is gone. So only those two terms left in the right-hand side. And the first part is for each individual, the deviation for each individual to its group mean. This quantity captures the variation due to the random sampling. This is the variation within group, right? For yij minus its group mean, this is calculated variation within group, within each group. We calculate the variation. The second part, we use the group mean minus overall mean. This quantity actually captures the variation due to a cross group. Okay, for using each group mean minus the overall mean, we square it, then take the summation. This is captured variation due to the group, due to the factor, we call it between sum of square, between group variation. So this is tells us what? The total variation for all the sample can be partitioned into two parts. One part is the variation due to the random sampling, the variation within group. And the second part is the variation between group due to the group factor. Is that okay? So this equation tells us the total variation can be partitioned into those two parts. Next, we're gonna compare those two parts on the right-hand side to determine whether those K group means they are equal or not. So here, remember what we want to do here. We want to perform a test on those hypotheses. The null hypothesis is all those K group mean, they are equal. The alternative is at least one group mean is different from the others. There are two pictures. The first picture, you can see the within group variation is smaller. Within each, there are three groups, right? Within each group, the points are clustered. The variation is small, right? And then you look at the group mean. Those three group mean, there are variation. The variation among those three group mean is large. That indicates what? At least one group mean is different from the other. So under this situation, when the between group variation is large and within group variation is small, we're gonna reject the null hypothesis. Does this make sense? What? So look at this picture. within each group, you can see for all the sample within group, they are clustered. Their variability is small. They are very concentrated, right? And with that, then this quantity for each individual minus its group mean gonna be small. This variation due to within group due to the random sampling gonna small. This part gonna small. For each group, you can see the within group variation is small. Then you look at the between group variation. For those three group mean, they are comparing to Y bar, the overall mean, their variability is large. This large gonna indicate by this quantity gonna be large. So whenever the between group variability is large and the within group variability is small, we're gonna reject the null hypothesis because that indicates those at least one group mean is different from the others. Look at the other picture. Here, within each group, their sample is widely spread. The variability for within group is large. And however, you can look at their group mean. They are close to the overall mean. The red line is the overall mean. They're all close to their overall mean. In this situation, when you calculate those two quantities, you will get a large between group variability and a small within group variability. Then this is indicate we're gonna accept the null hypothesis. Those group mean are quite similar. So this is the basic idea for ANOVA. Yeah.
Got a question just about formality. Does your null hypothesis always have to be the hypothesis in which all the means are the same, or?
Yes.
So if this was an experiment where you want to treat different groups, your null hypothesis was always that there's no outcome or no difference?
You mean the null hypothesis?
The null hypothesis is always that there's no difference.
Yeah, always no difference across those K group. And the alternative is that because this is an ANOVA test, it's an overall test. Just overall whether there's at least one group is different from the others. Okay? Did you get this basic idea for the ANOVA? Just comparing this within group variability and between variability. It's gonna indicate whether at least one group mean is different from other or not. So now we're gonna see how should we implement this idea into some mathematical formula. We already seen that the total variation can be divided into those two parts. The variation due to factor, we call it between group variation. And the other is a variation due to random sampling, is within group variation, right? For each part of it, there are different names for them. For this one, the between group variation could be called sum squares between, sum squares among, sum of squares explain. And this one is the other names for the within group variation. And also you should notice I put the degree of freedom under each of those three terms. For the total variation, for the total sum of square, its degree of freedom is the total sample size minus 1. Because when we calculate this one, we minus the overall mean. We use up 1 degree of freedom to calculate the overall mean. So here, the degree of freedom for the total variation is the total sample size minus 1. And the degree of freedom for the variation due to the group factors or between group variation is the number of group minus 1. The other one is just the total sample size minus number of group. Now let's look at each of those three quantities in details. How to calculate the total sum of square is the summation through 1 to k group, and in each group we do the summation through all the observation using each specific observed value minus the overall mean, then square it. This is give you the total sum of square, total variation. That okay? Y bar here is the overall mean. You take the average of all the sample across k groups. Is that okay? This is total variation. And here just a picture for the total variation. Just calculate for each individual point what's its distance from the overall mean, represented by this right horizontal line. So this is the quantity for total sum of square, total variation. Here we calculate the between group variation across those k groups. For each group, we need to calculate their group mean first, yj bar. Then we're using each yj bar minus the overall mean, looking at the difference from each group mean to the overall mean, square it, do the summation over all the observation. This gives you between sum of square. Okay? Then within group variation is the calculation within each group. Within each group, you're using the individual observation, each individual value minus its group mean. Square it. Here I missed a square here. There's a typo. I'm gonna correct the slides after the lecture and upload the updated version. Here's the square. And then this is calculated within sum of square, within group variability. Is that okay? So after we calculated those three sum of square, we need to divide each of them by their degree of freedom respectively. For the between mean squares, we call it between mean square. It's the between sum of square divided by its degree of freedom. It's a number of a group k minus 1. Within mean square, within group mean square is the within sum of square divided by its degree of freedom n minus k. The total mean square is the total sum of square divided by n minus 1. For all of those quantities, we summarize all of them into this one-way ANOVA table. It's a very important table. You should understand each element in this table. So the first column just tells you the source of variation. The first row is a between group variation. Then within group variation, the sum of those two parts is the total variation. Then the next column is sum of squares. I just show you how to calculate the sum of squares. This belongs to the between group sum of square and within group of sum of square. Actually, if you calculated those two terms, the summation of it should equal to the total sum of square. Okay? If you got those two cells, the summation of them should be equal to the total sum of square. And then you list the corresponding degree of freedom here. The first one for the between group is always the number of group minus 1. Within group is the total sample size minus number of group. And for the total sum of square, its degree of freedom is n minus 1. Also, those two degrees of freedom, k minus 1 plus k minus k, equals to n minus 1. Okay? The degree of freedom for between group and within group, the summation of them should equal to the degree of freedom for the total. If you got those two columns, then you can calculate the mean sum of square. Just using the sum of square divided by its degree of freedom. BSS divided by k minus 1 is the between mean square. And within mean square, just this quantity divided by n minus k. So we're gonna compare those two mean square, mean sum of square. The last column is called F statistics, F ratio. This F statistics is the ratio of BMS, the between group mean square divided by within group mean square. This ratio gonna tell you which variability is large. If this ratio is very large, that indicates the between group variation is big, and within group variation is small, that's gonna indicate you're gonna reject your null hypothesis, right? Whenever the between group variation is big, those group mean there are great variation among them, you're gonna reject the null hypothesis. If this F ratio is small number, that indicate between group variation is small, they're all close to the overall mean, and within group variation is large, they cross all those range, that indicate you do not reject the null hypothesis. Or group mean is close to the overall mean. So just depends on this ratio, you can see whether we're gonna reject the null hypothesis or not. So again, for this ANOVA test, the test statistics, we call it F statistics. It's defined by the ratio between mean square, mean sum square, divided by the within mean sum square. And this quantity is followed to a F distribution. Any F distribution is determined by two parameters. It's given by those 2 degrees of freedom. This degree of freedom 1, just the degree of freedom for the between group degree of freedom. Degree of freedom 2 is the degree of freedom for the within group variation. Okay, from that table, you got those 2 degree of freedom, right? The F statistics follow under the null hypothesis, gonna follow a F distribution with degree of freedom 1 and 2. So after we know those 2 parameters, we can give the distribution for this F statistics. And we just said that F statistics, the larger value of F statistics, gonna indicate you're gonna reject the null hypothesis. So how large is large? We need to determine this critical value, FU. What parameter determines this FU is the level of significance, 5%, and the sample size. Okay? So FU, this critical value, after you determined based on this alpha and N and K, which tells you the 2 degree freedom for this F statistics, you can get the exact value for this FU for 5% significance level. Let me finish here. Then you can see the right upper tail, you define the rejection region. Okay, what's your question?
But does this take into account if both the between both the BMS and the W, if both these values are very small, then you can get sort of arbitrary values for the F distribution, right? Is there any sort of additional test that sort of checks that beforehand?
Yeah, just now I just tell you intuitively, one value is large, the other is small, it indicates its F value. So finally, it's determined by the ratio of it. So if it's both small, still look at the ratio. If they're both small, they have the same magnitude, they could be a number around 1, right? Around 1, you will see that around 1 is usually it's a very common value for that F statistics. It's in acceptance region. It's not in the rejection region. We do not reject the null hypothesis.
So
It just depends on this F statistics, F value.
So you're saying that's usually not a problem if you have very small variations. This type of test accounts for that.
Right. Here is you are bringing up one question about this hypothesis testing. See, when we reject the null hypothesis, we have confirmative conclusion. We reject the null hypothesis. We identify significant evidence to support our alternative hypothesis. We get a very confirmative conclusion there. However, sometimes we cannot reject the null hypothesis. That is the situation you are talking about. In that situation, we have no conclusion. We just say we don't reject the null hypothesis. We don't say we accept alternative hypothesis, right? This is maybe the sample size is too small. There's no strong evidence to support my alternative research hypothesis, right? Okay. So after we identify this critical value FU, we identify this rejection region. Then we can we can compare our F statistics to this rejected region to determine whether we're gonna reject the null hypothesis or not. Okay? So let's look at one example. Here you want to see if 3 different golf clubs yield a different distance. You randomly select 5 measurements from each group. At the 5% significance level, is there a difference in mean distance? So there are 3 groups. You are comparing 3 group mean. So to perform the ANOVA test, within each group, you first calculate the group mean for all of them. Group mean for the first group, second group, and the third group. Take the average of those 3, you get the overall mean. Okay? So the data represented in the picture, just like that. You calculate the group mean for club 1. This is the group mean for club 2, for 3. Then take the average of them, you get the overall mean. So here just the group mean and the sample size within each group. The overall mean, the total sample size is 15, k equal to 3. There are 3 groups. Then using those numbers, you can first calculate the between group variation. And within group variation, the summation of them actually is the total variation. Sorry. Here. Then you divided each sum of square by its degree of freedom. You got the between mean sum of square and within group mean sum of square. The ratio of those 2 quantities is your observed F statistics. It's 25.275. Is this clear for this flow, for this calculation flow? So here, we put everything in this sheet. Under the null hypothesis, we are testing whether all of those 3 group mean they are equal or not. And the alternative is that at least one group mean is not equal to the other. And using the number of group and the number of total sample, you can figure out those 2 degrees of freedom, k minus 1, n minus k. Okay? Then for the critical value, you can use this F inverse function to get the critical value for those 2 degrees of freedom is 3.89. From previous slides, you observed the F statistics is 25. It's far larger than 3.89. So we're gonna reject null hypothesis. The conclusion is that there's at least one UJ is different from the others. Is that clear? Put everything in the table. You should get this table, result table. All your sum of square, degree of freedom, mean sum of square, F statistics, and the p-value. And then, actually, if you're using the Excel ANOVA single factor analysis tool, here is your 3 group data. You select those 3 group of data in this input range and indicate the column tells you 3 different groups. You click OK. It's gonna give you this ANOVA output. But it is very important for you to understand the meaning for each cell in this table. Is that okay? So using any statistical software, implement ANOVA analysis, it's gonna give you this table. For this table, after this lecture, you should understand what is the sum square, what's the difference between group variation and within group of variation, how to read this F statistics, and what's this p-value. The p-value is smaller than 5%. That indicates your ANOVA test is significant. You're gonna reject your null hypothesis. Is that okay? So this is really clear, right? So for the ANOVA test, then after you perform the ANOVA test, if you reject your null hypothesis, one natural following question is that, which one is different from the others, right? Yeah, you definitely need to know after you do this overall group test, perform the ANOVA. If it's significant, that indicates some of them is different from the other. Here is, for some example, there are only 3 groups. In some genetic world, there are 10, maybe there are hundreds, thousands different groups. You perform the ANOVA if the test is significant. So how to identify which one is significant? We call it the post hoc test. After the ANOVA, you always need to perform that test to identify which group is different from the other. Usually, this post hoc test just do the paired test. For any pair of them, they check the difference between those 2 group mean to see whether they are different or not. And there is a different algorithm to correct this multiple comparison. So if you go to the wiki to search the post hoc test, there's a number of different post hoc tests. For this one-way ANOVA, I suggest you use the Tukey honestly significance difference test, HSD test, post hoc test. By implement this procedure, it's gonna tell you which specific group is different from the other. But in Excel, this Tukey test cannot be implemented. But for any statistical software, such like SAS, S+, or SPSS, after the ANOVA, you can call this post hoc option to perform the post hoc test to identify which one are different. Yes?
So just to clarify, the F statistic that you generate
Mm-hmm.
from the WMS over the BMS, that's going to give you, or between MS over WMS, correct?
Yeah.
That's going to give you an F value, and if that exceeds your critical F value, that allows you to say that you have a significant difference. There's going to be a significant difference between groups somewhere within your data set. Is that correct? Because you're taking that into account of the within differences, correct? Like I've always go to a post hoc test to tell me if there's a difference if my F value tells me there's a significant difference, but that number is telling me that there's at least one between group difference that is significant within the value set. Is that correct?
You mean after?
Or is it just it's telling you that there is of the variance within all your entire sample that there is a difference? I guess my question is what is specifically is that F value telling you, or if your F value over your critical F value, what exactly is that telling you to then go to the post hoc test?
This value, when you're comparing F value to this critical value, just show you whether you're gonna reject your null hypothesis or not.
Right.
If in the rejection region, you reject your null hypothesis. When you reject your null hypothesis by using the ANOVA test, what's the meaning of it? We claim that at least one group mean is different from the other.
Okay. And then that's where you go into. So that really
Yeah, you're gonna go into search.
Post hoc obviously gives us where that's.
Yeah. If not significant, it's not necessary to use the post hoc. Yeah.
So if you had, let's say you had 15 time points of single variable
Mm-hmm.
using a one-way ANOVA,
Mm-hmm.
14 of them are exactly the same, but there's very little difference, and you have one that's very different.
Right.
Theoretically, your F value or your F statistic should be able to tell you if that one group is significantly different, identify it, and then in the post hoc test you find it.
Right. The example you are talking about, you said about 15 time point. This is for the same subject. This is not good for the ANOVA test because the ANOVA test require each group are independent. That one you need to use the repeated ANOVA.
Oh, right.
There are correlation between different group. But yeah, there are multiple group. You first apply ANOVA, this overall test, to see whether there's some difference among group. If it's significant, then you go next to do the post hoc test to identify which one is different.
Is the post hoc test different from like an iterative pair sample?
Yeah, it's different.
Okay.
Yeah, for the pair, if you start with that paired two sample t test, you just first of all the variance, the calculation for the variance, overall variance is different. For that one, you just using the variance from those two groups. But for the post hoc, actually, they are using all the sample to calculate the variance. And also the post hoc test, they also adjust the multiple comparison. So you are doing 15 different paired tests. They're gonna adjust the overall experimental significance level. So there are lots of details in the post hoc. You need to use the specific software package to get the outputs. Yes.
Can you use ANOVA for as in you're looking at more like between samples? Can you use it as a population study? You know what I'm trying to say? Because you're looking at maybe let's say n equals 5, basically picking 5 samples from each population, and then you compare between the samples, and you say there is a, let's say there is a difference between the mean. But then do you need to be, let's say the n must be bigger than 50 to justify between populations?
You mean the sample size?
Yeah, do you need to have
The underlying assumption for ANOVA is that the number, the underlying distribution should approximately normal. If it's those numbers, if the underlying distribution is approximately normal, the sample size doesn't matter. They can deal with the small sample size.
So you don't have to worry about the, let's say it's biased because you pick 5 numbers that's maybe different.
Yeah, as long as this measurement is normally distributed, yeah, 5 is okay. Yeah, any other questions? If no question, then this is for today's lecture. And so, yeah, this is gonna be the last lecture for the statistics. So if you have any questions, you can go to the tutorial for the TA session, yeah. Or if you want to talk to me, you can send me an email to schedule an appointment. Anything else? Okay.
How many people are coming to it? I don't really care. I just want to tell the other people to show up if they have to show up.
If you have questions, need help for your homework to prepare for the final.
This stuff is a lot more straightforward than Python.